This lecture should get you through chapter 23, which is the circulatory system or cardiovascular system, whichever one you want to call it is just fine. It starts out by asking you to define the heart. It is made out of cardiac muscle. Its job is to pump blood throughout the circulatory system so that we can deliver nutrients and respiratory gases. We can get waste out of the body, all that sort of jazz. And so this is it. This is the pump. Blood is what's going to be transporting all of those substances that I just mentioned a second ago. So the respiratory gases we talked about in the last chapter, that's oxygen and carbon dioxide. There are a bunch of clotting factors that are in the blood so that if you get a wound like this person apparently has, you will stop bleeding after a little bit. We've also got immune cells like white blood cells in there, and then immune chemicals like cytokines and interferons that are circulating within your bloodstream as well. So within the animal kingdom, there's a couple of different ways you can do a circulatory system. There's open or there's closed. Open circulatory systems means that the blood vessels are actually open-ended. So while we have pumps, the blood gets pumped out of the vessels and then it mixes with the fluid out here. So it's not really called blood, it's called hemolymph. And then that fluid just gets circulated, it gets picked back up, and then it gets dropped off again. It's not as efficient a system as a closed circulatory system is, but if you remember, the critters that have these open circulatory systems, their respiratory system doesn't really need the circulatory system, so this works for them. Closed circulatory system is what we have. It's called closed because all the blood vessels are closed. The blood stays in the blood vessels, barring injury at all times. So this is what vertebrates like fish, amphibians, reptiles, and you all have. Closed circulatory systems are more efficient, and they need to be because our respiratory gases are going to be transported within that blood. From there, blood vessels have different names, essentially depending on the direction that they are taking blood. So arteries go away from the heart. If it helps you to remember it, artery and away both start with A, so they go together. Veins take blood back towards the heart. Generally speaking, when you see textbook pictures of the circulatory system, arteries are usually red, veins are usually blue. The thing is that color isn't actually denoting arteries and veins, it's denoting oxygenated blood and deoxygenated blood. So the pulmonary circuit actually reverses the colors, where the pulmonary artery is actually the blue one, and the pulmonary veins that take blood back to the heart, they're red. So the pulmonary circuit, the colors are backwards. But remember, the colors are about whether there's oxygen in the blood or not, and so that's what that's trying to show you. Capillaries are the vessels that actually participate in exchange of materials, and so what that means is this is where diffusion of oxygen and carbon dioxide actually occurs. This is where nutrients get on board in the digestive system. This is where wastes get on board at all tissues so that we can deliver it to the kidneys so that the kidneys can get rid of it. So capillaries, even though they're the smallest vessels, they're arguably some of the more important ones because they're the ones that are actually exchanging materials between cells in the bloodstream. When you start talking about heart chambers, different types of animals have different numbers of chambers. We're just going to essentially look at what's going on in our circulatory system. So our heart has 4 chambers. We've got 2 atria. They are the receiving chambers, and they're the superior part of the heart. And then we have the ventricles, which are the actual pump part of the heart. They are the inferior 2 chambers. Now, the directionality always seems like it's reversed for students, but you've got to remember that this is a heart that's in somebody's chest, and if this was in my heart, this would be my right side. So this is the right atrium, right ventricle, left ventricle. The way the blood pumps through the heart, it goes from an atrium to a ventricle and then out someplace, depending on which side you're on, and then we come back through an atrium to a ventricle, and then we pump out again to whichever part we're supposed to go to from there. There are also other vessels that we didn't talk about earlier. So there are smaller arteries that connect large arteries to capillary beds. They're called arterioles. And then there's also venules, which we'll get to in a second. So capillary beds are really how capillaries exist. They don't exist individually like this picture is trying to show you. There would be another capillary here and another capillary here. And so you end up with a bed of capillaries that are taking all the necessary nutrients to every single cell, not just these 4 cells. These cells need stuff too. Venules drain blood from the capillary bed, and then a bunch of venules merge together to make veins that are going to take the blood back to the heart. Double circulation means that our heart is essentially 2 side-by-side pumps. The right side of the heart is what's known as the pulmonary circuit, and P.S. you are just getting the words in red to fill in the blanks here. The left side of the heart is what's known as the systemic circuit. It pumps the blood to all the body systems. That's why it's called the systemic circuit. So you're just getting those two words that I just mentioned a second ago, but make sure you do that. From there, what I tell you you need to be able to do is trace the flow of blood through the heart. So I'll run you through this cycle a time or two. So let's say that we're coming back, the blood was just up in your brain. We're going to come down through jugular veins into the superior vena cava, which takes blood into the right atrium. The right atrium pumps the blood through the tricuspid valve, which is also known as the right atrioventricular valve. And then from that valve, we go into the right ventricle. The right ventricle is going to pump the blood through the pulmonary semilunar valve to the pulmonary trunk, which splits into the right and left pulmonary arteries, which are going to take us to the lungs, where we're going to pick up oxygen. We're going to come back from the lungs through oxygenated pulmonary veins into the left atrium. The left atrium is going to pump the blood through the mitral valve or bicuspid valve or the left atrioventricular valve into the left ventricle. Left ventricle is going to pump the blood through the aortic semilunar valve into the aorta, which is the largest vessel in terms of diameter in your body. It also has the highest, pressure of blood within any of the blood vessels in your body. So that's the pathway that goes through there. What you guys need to be able to do is, like, if I ask you, there's a blood cell that's currently in the right ventricle, where does it go next? You would need to know it's going to go through the pulmonary semilunar valve next, and then into the pulmonary trunk. By contrast, I could say a blood cell is currently in the left ventricle. Which valve did it just pass through? You would need to know the mitral, bicuspid, or left AV valve. Now, another little side note, whenever you're looking at a heart, the left side of the heart is always going to have a thicker muscle wall to it than the right side of the heart, and that's because the workload on the left side is actually much more difficult. This side of the heart has to pump the blood up to the brain against gravity and down to your big toe with enough force that it can come back up later on, and so this side has to work a lot harder. This side only has to pump the blood to the lungs, which are literally right here and right here. It's not really all that hard, so it doesn't need as much muscle in order to be able to do that. So if you're looking at a heart on some test and nothing is labeled for you and you just have to know everything, which is how tests are generally going to work, look for that thicker side, and then you know that's the left. Once you know your left side from your right side, then you know the atria are going to be on top, the ventricles are going to be on the bottom, and then from there it's just a matter of filling stuff in. Okay. Next up, I said be able to explain the cardiac cycle. There's a couple of words that are going to matter here. Diastole is relaxation of a heart chamber. During diastole, that's when the chamber is filling with blood so that it's going to be able to pump blood when it starts to contract. Systole is the scientific word for contraction. So this is when the heart's actually working as a pump and it's pumping the blood that had filled into the chamber during diastole out of the heart and getting it off into circulation. Cardiac output is the amount of blood the heart can pump in 1 minute, and generally speaking, for a person at rest, it ends up being your entire volume of blood every minute. And so your heart is a very efficient pump that can get things out into circulation fairly well. Next up, heart rate is also known as your pulse, and so they are both the exact same thing. If you're going to actually calculate a heart rate or a pulse accurately, you would want to feel for a full 60 seconds how many times your heart beats within that time period. That said, most medical professionals don't actually count for the full 60 seconds because, you know, they've got things to do, so they're not really taking a lot of time to feel that or to feel it for the full 60 seconds. So you can also feel it for 15 seconds and then multiply that number by 4, and it gets you to the same thing. It's just not quite as accurate. From here I gave you this picture. I've already talked about most of the stuff that's in here. I do want to focus on a couple of things that I don't like the names they give you right here. So first one that I want you to come down to is what they have called right AV valve. And next to this one I want you to label it tricuspid valve. That's what most people usually call it, is a tricuspid valve. They've already done that one correctly. So next up, come over here to the left AV valve. This one has multiple names, like it has 3 names. The one that they're calling it here, or it's also called the bicuspid valve, or it's also called the mitral valve. Mitral is M-I-T-R-A-L. Most of the time doctors are going to call this the mitral valve. Everything else is okay in terms of names. Notice you can still see the wall is thicker on the left side than it is on the right side. So yeah, make sure you get that labeled, pause it so you can get stuff done. Function of the heart valves is to ensure one-way flow of blood. So essentially, whenever let's say your right ventricle pumps the blood out into the pulmonary trunk, when it relaxes again, the blood wants to fall back down into the right ventricle, and that's not okay. It would make the heart pump the same blood over and over again. So what happens is when the right ventricle contracts and the blood starts to fall back into it, the pulmonary valve shuts so that the blood can't continue to fall back into it. So that's what the heart valves are doing, is making sure the blood can only move forwards and it never backs up into a chamber it had just gotten pumped out of. All right. I went the wrong way, sorry. We can't really do the activity, so I'm just going to skip right past that. Heart murmur is what you guys have next. So a heart murmur is a heart sound that is not supposed to be there, and it is usually indicative of one of your valves isn't closing like it's supposed to. So I don't know if you guys have ever listened to what a heart is supposed to sound like, but it's usually described classically as lub-dub. If you hear lub-dub, there's blood that's whooshing through some of our valves when it's not supposed to be anymore, and that's what a heart murmur is. Robin Williams had a heart murmur prior to his death, and he actually had his bad heart valve replaced with a cow heart valve. It works the same way as ours, and so that's what he chose. You can also choose pig. You can choose a mechanical valve. Mechanical valves have this weird quirk of you can usually hear them closing, and so people often choose like the cow or the pig because it's quieter as it works. How does the heart maintain a rhythm? It does that because it has its own pacemaker that's called the SA node. The SA node fires off impulses. They get relayed through another node called the AV node, and then that makes the ventricles contract off over here. So this is what's known as the intrinsic cardiac conduction system, and what it amounts to is the heart keeps its own rhythm because of the SA node. Now the nervous system can speed things up or slow things down, but the heart can do its own thing because it doesn't really need to be told to do anything by the nervous system. EKGs are what help us determine whether or not your heart rhythm is working like it's supposed to, and you guys are non-majors, you're not going to have to read this, but there's 3 deflections that you should typically see. There's the P wave, the QRS complex, which is the big spiky one, and then there's a T wave. The P wave occurs because the SA node is firing, the QRS complex occurs because your ventricles depolarize, and then the T wave occurs because your ventricles repolarize. This is what's known as normal sinus rhythm. This means your sinoatrial node is doing everything like it's supposed to, and your heart's contracting like it's supposed to. Flatline, you see on TV shows all the time, a person will flatline and then they'll be like, grab the paddles. That's not how it works. You can't start a stopped heart by shocking it. You have to have what's known as a shockable rhythm in order to defibrillate a person, and a flatline is not a shockable rhythm. You can still try CPR and see if you can kind of beat the heart back into beating, but shocking it does not make it work. It's flatlining. AED is what you would give to a person who has that shockable rhythm that I was just talking about a second ago. The AED, that's what it stands for, automatic external defibrillators. Not that it matters, but we have some on campus so that if we had a student who was fibrillating, we could help them out. But what you do, you turn the nice little machine on, you put these pads on exactly where the stickers show you. The machine tries to detect whether or not the person actually has a shockable rhythm. If they don't, it will not shock them. If they do have a shockable rhythm, these are the paddles that you always see in the TV shows where the person's like, clear, and then they shock them and the person jolts and then they magically come back to life. And so this is a defibrillator that can help those people who have a shockable rhythm but not a flatline. Next up, I don't know why it doesn't like to work on those questions, but you have coronary circulation apparently being discussed next in the notes. I'm looking for where this is and I don't actually see it, but here's the thing. Your coronary circulation supplies the heart with a functional blood supply, and when I say functional, I mean it's oxygen rich, carbon dioxide poor, nutrient rich, there's not a lot of waste in it. Despite the fact that the heart is filled with blood all the time, the blood that's in the heart doesn't actually serve the heart's purposes. And so this is the blood supply that keeps the heart itself alive. So when a heart attack occurs, what happens is that coronary circulation from a second ago gets broken somehow. Either a clot gets stuck and so blood can't move past that clot, or maybe an aneurysm ruptured and so you're bleeding out of this hole and then this tissue is not getting functional blood. When you don't get functional blood, that means the heart tissue starts to die. And if you remember last semester, if you damage heart muscle, cardiac muscle, it cannot repair itself. And so that damage is permanent and it hinders the ability of the heart to pump effectively. And so that's why heart attacks can kill. It's because the heart's not a very good pump anymore. Stroke is essentially the same thing. It's a clot or it's a ruptured aneurysm, but it's in the brain now. So any tissue death that occurs is happening in the brain, which is also amitotic and doesn't heal itself very well. Although sometimes some other areas of the brain can take over the functions of that. Here we've got a clot that's stuck and some plaques that have developed because the person has atherosclerosis. This is one of the reasons why atherosclerosis increases your risk of stroke and heart attack. When you get these plaques build up in the wall, it makes it more difficult for blood to move through the vessels without starting to form clots that they weren't supposed to make. So this is what a picture of that atherosclerosis looks like under a microscope. That cartoony picture from a second ago also got there. You're putting down the things that you should do so that you can reduce your risk of developing atherosclerosis, which it's always diet and exercise. All right, coming back to the blood vessels from earlier, these are just the highways that the blood's going to be traveling on. We already defined arteries and veins earlier. We're just kind of going over a little bit of the differences between them. So arteries have this thick layer of smooth muscle that can help them do something called vasoconstriction that can increase your blood pressure if you needed to increase it, like let's say you're exercising. Veins, on the other hand, have a much thinner layer of smooth muscle. They can still vasoconstrict, they're just not as strong at it as the arteries are. Also, very importantly, kind of like the heart, the veins also have valves to make sure that blood doesn't fall back down after it's moved past a certain point. So if you see a blood vessel that has a valve in it, it's got to be a vein because arteries don't have those. Notice the color in the capillaries, it's kind of switching between red to blue, and that's because that's where we're dropping off the oxygen and picking up the carbon dioxide. All right, make sure you did get those words in red to fill in your blanks up there. Blood pressure is the pressure of the blood within your blood vessels. The heart is what generates blood pressure, and then your arteries and veins help regulate your blood pressure. Average changes depending on which textbook you're using, but usually doctors say your average blood pressure should be 120/80. 120 is what's known as your systolic pressure. That's the pressure that's generated as the heart contracts. But even when the heart's relaxed, pressure doesn't bottom out to 0. And so the lowest the pressure should be is this 80 that it's showing you right here if you happen to have what is known as average blood pressure. Pulse, I discussed that earlier. The place where pulse is usually measured is where I'm showing you right here. This is on the radial artery. If you can't feel it there, you can go to the GIF that I showed you earlier where the dude was holding his fingers up to his neck. You can feel it in the carotid arteries as well. You use your 2 fingers just like they're showing you here in this picture. Don't use your thumb. Your thumb can also have a pulse and it will make you double count so that your count is artificially high. But what you do is you just feel how many times can you feel the little thump. How blood pressure is measured. This is something that I usually have students do in class, but of course we can't do that right now, so I'll just describe the process to you. You put a sphygmomanometer, which is the fancy word for a blood pressure cuff, around a person's usually upper arm. You can put them in other places to get measurements though. You use the little bulb to inflate the cuff, and essentially what you do is you create a tourniquet with the cuff so that blood is not able to move past that cuff. You start listening with the stethoscope, and then you start to slowly release the pressure, and there will come a point where the pressure of the cuff is the same as the pressure of the blood in this artery, and so blood will start to squirt past this, and so you start to hear the pulse in the stethoscope, and the first moment you hear the pulse, that gives you the top number of a blood pressure reading, or the systolic pressure. Then you keep listening, and there comes a point where the cuff is not obscuring blood flow at all, and so you stop hearing sounds. The first moment you realize you don't hear a sound, that gets you the diastolic pressure, which is the lower number in a blood pressure reading. Hypertension is high blood pressure. They did just change the recommendations for this. It used to be if you had a systolic pressure that was over 140, you were considered hypertensive. Now, if you have a blood pressure where the systolic pressure is greater than 130, you are considered hypertensive, and they want you to either try diet and exercise to get your blood pressure lower, or they want to put you on meds to get your blood pressure back down. Again, we can't really pair up and do this, but you can try to get people in your family to have them take your pulse and you take their pulse, and then do the exercise thing that I've got at the back of this chapter. The assignment that I'm going to post for you guys, I haven't really decided yet, but it might be a quiz where you're going to be graphing pulse before and after exercise. It might be a coloring thing. I really haven't decided what I want to give you guys for a quiz yet, but try practicing taking a pulse. It's something that can help you if you ever end up having to call 911 because a family member is unconscious. The more information you can give the medics when they get there, the more they can do to help your loved one. And so taking a pulse is something that really everybody should be able to do as a just in case. Is blood glowing everywhere all the time? No. Essentially, you don't have enough blood to send it everywhere all the time, so you send it to the body parts that need it right now, and then once those body parts are done, you send it to the next body parts that need it right now. Let's see, after that, how are capillaries unique? They are the smallest blood vessels, they are the thinnest blood vessels, and they're the only ones that actually exchange materials between the bloodstream and then the tissues outside of that. This picture is trying to show you how you regulate where blood's going. So if you're actively using a tissue, these little sphincters are open, blood is moving through the capillaries, we're exchanging materials. But if you don't need to send blood to an area, the sphincters constrict, they cut off the capillary bed, and then blood just skips that tissue and then moves to a place where it's needed at that point. Plasma is the liquid component of blood. There are a lot of things that are transported in the plasma itself. There's a bunch of clotting factors and there's a bunch of immune factors in the plasma. So it's important that you know while it is mostly water, it is not all water. There's a bunch of stuff in there that is critically important for your health and well-being as well. Red blood cells are also known as erythrocytes. They really have one job, and they do that one job really well, and that is transport oxygen around in the body. White blood cells. There's different kinds of white blood cells. Their fancy name is leukocytes. Generally speaking, most of your white blood cells are phagocytes, and so they eat things. And so this one is chasing down a couple of little bacteria, and then it eats them once it catches them. And that's how most of your white blood cells are going to work. Platelets are not real cells. They are pieces of cells that normally float around in a sort of broken state. Whenever a blood vessel gets damaged, like there's a tear in this blood vessel, chemicals get released from the damaged tissue and it activates platelets so that they get really sticky, and then platelets start to stick together to cover the hole so that you stop bleeding to death, essentially. What are phagocytes? They're eaters. They just run around and eat stuff. So this is what all your white blood cells are capable of doing, although some are better at it than others. Anemia is a symptom of you not being able to transport oxygen well enough in your body. There are lots of reasons why a person might be anemic. The most common reason that a person is anemic is iron deficiency. So if you don't get enough iron in your diet, you can't make hemoglobin correctly, and so you can't transport your oxygen. And so usually they'll tell you to try like an iron supplement or eat a better diet so that you get more iron. That said, there's other reasons. You might have hemolytic anemia, you might have pernicious anemia, you might have sickle cell anemia. There's different forms. It's just that the most common is that iron deficiency anemia. EPO is erythropoietin. It's a hormone that does get produced by the kidneys whenever the kidneys start to feel like they're hypoxic, which means they're not getting enough oxygen. What the hormone does is it travels from the kidneys to the bone marrow, and it asks your bone marrow to, hey, speed things up. Can you make red blood cells a little bit faster so that you can start transporting oxygen better? If you have ever traveled from here to like Denver, Colorado, you start to get altitude sickness because the air is thinner up there. Well, after a few days, your kidneys have started to up the production of EPO, so your number of red blood cells has actually increased while you've been up there. And so after a few days, you notice you don't feel kind of as short as breath or as headachy as you did the first few days. And so EPO is the hormone that helps you get over that altitude sickness. That said, there are people who take EPO for, I'll say, nefarious reasons. Lance Armstrong is, of course, like the name that everybody knows who was blood doping. What I want you to understand is blood doping has significant risks associated with it. It creates something known as polycythemia, which is a high hematocrit, or otherwise known as you have too many red blood cells. The problem with that is it makes your blood extra thick, which I want you to imagine that your heart is trying to pump like cold maple syrup over your bloodstream, and that helps you see why having extra thick blood is difficult. Your heart has to pump harder to pump that thick sludge through your blood vessels, and so it's not good to make your heart work harder like that. The other thing is it makes clotting way more likely to happen, so again increases the risk of stroke and heart attack like we talked about earlier. So if you are bleeding, there are several things that your body does to help you stop bleeding. Number one is vasoconstriction. You'll constrict the smooth muscle around the blood vessel enough that you actually do what I like to call kink the hose. If you kink a garden hose, does water still come out the other side? Either flat out no because you kinked it well, or at least if it does come out, it's coming out in much reduced quantities. So this slows the loss of blood. And it's the very first thing that your body does whenever you get an injury. At the same time that vasoconstriction is happening, we're also starting to activate platelets in the area. And again, those platelets, once they're activated, get sticky. It's going to take a while to build up enough of a platelet plug for us to sort of cork the hole so that we stop bleeding. But this is working at the same time as vasoconstriction. It just takes longer to create that plug. After that, there's another very complicated chemical cascade that happens where normally in our blood we have this protein called fibrinogen floating around, and it's dissolved in the plasma and you can't see it. Well, whenever you injure a blood vessel, lots of chemicals get released that start this chemical cascade, and one of the steps in that cascade is it converts fibrinogen into fibrin, which is this brown net that you see right here. Essentially what it's doing is it's turning your liquid plasma into a solid so that your plasma is not leaking out of that area anymore either. Stem cells live in the bone marrow, and they make all of your blood cells. Red blood cells, white blood cells, and platelets all come from the stem cells that live in your bone marrow. If some of the stem cells, or even one of the stem cells in the bone marrow, starts to do mitosis more often than you want it to, you can develop leukemia or other blood cancers. In this case, I'm going to back up for just a second. Let's say that this cell becomes cancerous and it starts to make too many of these cells off down here. That is a type of leukemia. It's sometimes called lymphocytic leukemia. If this one becomes problematic, you're making too many of these cells, that's a different type of leukemia. So there's different types of leukemia that develop depending on which one of the stem cells is actually the one that's started to make an army when it was not supposed to. Do notice that leukemia is not something like you have it for a couple weeks and then you're all better. You have to get treatment or you'll die. And in a lot of cases, even with treatment, you'll die. Leukemia is really tough to treat. And the problem with it is if you have it, the white blood cells that you're making don't work like they're supposed to. And so you're going to get really frequent infections that you can't heal from because you essentially don't have an immune system anymore once you get leukemia. So if you have people in your family who are super sick all the time, maybe they're losing weight, they're feeling tired all the time, it's always a good idea to go in because this needs to be treated quickly. Otherwise, it becomes very difficult to treat. Good luck.